The idea of a differential equation is really similar to like vectors, when you did vectors in HAM or parametrics. It's where you can isolate different variables and look at how if I keep everything else the same, if I just isolate how that variable is changing, how does it impact the whole situation? So in vectors and parametrics, that allows you to like separate horizontal from vertical movement. When you get into 3D vectors, then you can do horizontal, vertical, and like, you could do like east, west, north, south, and up, down movement, and you can start to really getting that gimbal idea, getting it all kept level, whatever. So in calculus, we're gonna look at it by separating anything that has a dx in it from anything that might have a dy or some other variable in it. So that's what a differential equation is. You can take in a whole college class for a whole semester just on differential equations. I still remember, I don't know why that sticks in my brain, like my DiffEQ class in college was Math 231. And so, yeah, it's a whole class just dedicated to that. We're just going to do one lesson dedicated to it. So we're not going to dive in it too deeply. Let's see. The strategy we're going to learn. So I'm all about things that'll help you remember. So the strategy is called separate and integrate. So we've got integral over interval, or just things that you can like, just a brain trigger to be like, okay, I know how to get started. So if it's average value and you think integral over interval, that's just the first, I just need to write down integral over interval, get the point for that, and then see what I can do from there. So the strategy for a differential equation is to separate and integrate the things together, which is kind of interesting if you think it from a historical point of view. Think back to what you learned in like US history and what we did in our country in terms of integration, right? Aren't those like separation is like separate but equal, and then integration was supposed to be the opposite of that, and we're bringing things, all mixed and back in together. And so the idea that we're doing those two opposite things in math at the same time, if you think about it from the language of it and like historically what that means. All right, so let me just talk with you about where we've seen this. We saw this when we did what we called implicit differentiation. When we were doing derivatives, we saw problems that failed the vertical line test and had x's and y's that could not be separated. You couldn't get y by itself, and we learned how to do a derivative that way. This is just the reverse of that. This is problems where you can't necessarily get the y by itself. So is it possible to do the integral when you can't get that alone? And so we're going to talk, that's what a differential equation is. So we'll learn how to manipulate a problem and how this strategy works. But the thing that is true about it is that it has to be, and I left blanks for you, this only works on products and quotients. Okay, it only works on products and quotients. So that's our first thing here, this method we're going to do today. And really, a quotient is a product, right? A quotient is just a product in disguise. You could turn it into a product, but it's only going to work on that. It doesn't work on addition or subtraction. We have other methods for addition and subtraction. So the idea of dealing with a product has lots of different ways you handle it. Okay, so up until chapter 6, every time you guys came up to a product, I would say you don't know how to do this yet. You don't know how to do this yet. We can do antiderivatives of sums. We could do antiderivatives of differences. We could do constants. But every time we got to a product, it was like, not yet. Now you've learned some of the ways to do products. So some of the ways to do products are use substitution, integration by parts, tabular integration. Those are all strategies to deal with products. And this is the last and final strategy. Okay, the idea of doing separate and integrate as a way to deal with products and quotients. Okay. So let's just practice the art of separation. Okay, this problem is a product. Therefore, it must be able to be separated. And we use cross multiplication to do that. So by separation, what we mean is that anything that has a y in it should be moved to one side of the equation, and anything that has an x in it should be moved to the opposite side of the equation. That's the art of separation. Okay, so we start that with cross multiplication. So that would be the first thing. So drop a 1 and do a quick cross multiplication. That's going to give you dy by itself, and then it's going to give you negative 2xy squared, but with a dx tagged on the end because of the cross multiplication. Now, everything that has x's in it is on the right side, but the y squared is on the wrong side. The y squared needs to be moved to the other side of the equation. So what's the easiest way to do that? Okay, to divide by y squared. And so then we're left with negative 2x dx. And then if possible, and it usually always is, you'll want to write this as completely as products. So we prefer not to leave a quotient in our, so we've got dy over y squared. It would be better for you to write this as y to the negative 2 dy and then negative 2x dx. So for the method we'll be learning today, so you'll want to write it like that. Now, have I done any calculus yet? What kind of math is this? This is just algebra. Okay, this is just algebra where I'm moving things around legally from one side to the other using all legal algebraic steps. Okay, let's try the next one. Separate this differential equation and then sort of if you can, if it's possible. Well, it's only possible if it's a quotient or a product. Is this problem a quotient or a product? I will argue that it is, yes, 100% a quotient or a product. Okay, there is, right? You've learned that any exponent written to the x minus y is the same thing as a to the x divided by a to the y. That's a rule for x. It's an algebraic rule. So subtraction from powers can always be turned into a quotient. So that means that it's possible for this problem that this can be written as a product or a quotient. So I'm going to come back to this and say, okay, dy dx is a quotient, and on the other side I can also write that as a quotient. And the quotient would have what in the numerator? E to the 2y, and then what in the denominator? E to the x, bless you. Once it's written that way, then you proceed with cross multiplication. That will give me e to the x times dy. And on the other side, it will give me e to the 2y times dx. So now I've successfully cross multiplied. However, the wrong things are on the right things are on the wrong side, or I need to have one side that's all x terms and one side that is all y terms. So I need to move this one over to the x side, and I need to take e to the 2y, and I need to move it over to the right side. Okay, anybody want to take a stab at what that's going to look like once I've moved them around? Okay, Rose.
dy over e to the 2y
Okay.
equals dx over e to the x.
Okay, so what algebraic step did you use?
Division.
You used division. I divided both sides. Okay, now would she want to leave that in that final form? Okay, still really don't want to leave quotients in their final form. All right, so one other person, somebody, what would it look like? Okay, Izzy?
E to the negative 2y.
Okay, e to the negative 2y times dy.
Equals dx, or e to the negative x dx.
E to the negative x times dx, okay? So that is how you're going to want to leave that. This is still the process of separation. We still haven't done any calculus yet. This is all just algebraic manipulation and moving things over to get it ready for the calculus step that would come next. So this is the separate part, yeah.
Could you also have it be when you switch them around?
Mm-hmm.
Be it e to the x over dx equals and then e to the 2y over dy.
You could, but then somehow you're going to have to get your dx and your dy, they need to be in the numerator.
They do.
Yeah, Yeah, the calculus doesn't work unless they're in the numerator. But one of the, you might notice this about the algebra, you said e to the positive 2y over a dy, and then you said e to the x over a dx, okay? So one of the algebra strategies then would be to take the reciprocal of both sides, which is legal. And so then that would put the dy over the e to the 2y, and it would put the dx over the e to the 2x, but you still then have to change them to negative exponents because you don't want it to be a quotient. Okay, all right, great. All right, how about this one? Example, our third one on slide 6. Separate the differential equation e to the 2y plus the value of x. Okay, is that possible to write as a product or a quotient? That's a sum. It's not possible. Now, if it had been written like this, e to the 2y and the plus x was clearly part of the power, that would be possible. Okay, because that addition turns into a product itself that can be multiplied. But when it's not clearly part of the power, the plus x is dropped down. Okay, this is a sum and it's not a product or a quotient. So this is not the right way. So this is not a product or quotient. So separation isn't possible. Okay. All right. The algebraic art of doing that is so important that I need you to practice that in small groups. It'll take you probably less than 10 minutes to do that. So if you'll go back to your module and find the in-class worksheet for 6-4 and then get into your groups of 3 and 4, I want you to work through, I've given you several examples, which ones are possible to separate, and if they are, do it, and which ones are non-separable, because the way they're set up cannot possibly be written as a product or a quotient. Okay, this is such a foundationally important skill that we're just going to take a moment to practice that. Okay. So now that you know that factoring is a key part of making things into either a product or a quotient, now we're ready for phase 2. So phase 1 is always separation. Phase 2 is always integration. So separate and integrate, or separation followed by integration. So we're ready to move on to this next thing. So a differential equation that comes in the form of a product is called separable. We separate the variables by moving all of the y's to one side and all of the x's to the other. The solution, so that's this next step that we're at here, the solution is found by anti-differentiating each side, and I love this, with respect to its thusly isolated variable. Isn't that a cool sentence? Okay, with respect to its thusly isolated. That means you've just done the isolation part of it, and so you're going to do the antiderivative of both sides. One side will have an antiderivative with the letter x in it, variable x. The other side will have an antiderivative with the variable y. Okay, so just for last things, separate followed by integrate. All right, let's do it. Okay, this was the first question that we saw, and we got it into its separation stage. So let's pick up where we were. We did the work already on this once. The separation turned out to be y to the negative 2 dy equals negative 2x dx. That was the separation. All right, our integrate stage comes where we apply an integral to both sides. So you're going to drop an integral on both the left and the right side. And then you're going to see what comes of it after you've done the integration. Okay, so on the y side of the problem, how do I do the antiderivative of that? Okay, add 1 to the power. So the power becomes y to the -1. And then what else happens? Okay, divide by that power, divide by -1. And what else happens when you do an antiderivative? Plus c. On the other side, we're going to do an antiderivative, but this time we're doing it with respect to the thusly isolated variable of x. And so it's going to be, what's the antiderivative? -2x. And what do we get for that? -x². And what else? A plus c. Now, how do we distinguish between our plus c's? So let's call it c1 on that side and c2. Oh, we will, but they don't cancel out because they're different c's. Okay. All right, so now our last step after we separate and integrate is to solve, because that's what the direction, yeah.
Wait, why isn't it divided by 2?
Because there was already this 2 right here. It was there and then I reduced it, so sorry. All right, our last step is to solve. That's the directions. To solve. To solve basically means get y alone. Or isolating y. So now we just are back to algebra again. So we literally start with algebra. We do basically 1 line of calculus, which is the antiderivative, and then we're back to algebra again by manipulating this to get y alone. So what I would start with is the fact that I would rewrite this as -1 as my numerator and y as my denominator, because I don't want negative exponents. I would subtract c1 from both sides. Now, do c2 and c1 perfectly cancel each other out? No, because I don't know what kind of constants they are, but I do know that if you take one constant and you subtract another constant, what are you left with? A third constant. Okay, if you want to call that the third constant, you can, or most people will just say it's just plus, we're just going to call it plus c now, because that's the only constant I have left. And then we have -x². This next step of continuing is where most people make their biggest mistake. What I most often see happen is that people are like, oh, I'm going to take a reciprocal. And then on the other side, I'm going to take a reciprocal, and I'm going to take a reciprocal. Okay, which violates a whole ton of math, but you could convince yourself logically that that must be the right thing to do, but it's not. So let's go back and do the correct algebra on how to solve that. The correct way to solve this would be to put a 1 under it so that they both have denominators. And once they both have denominators, then what do you do? And it's really a cross multiplication problem. Okay, if you've got a denominator on one side, you want to get a denominator on the other so that you can cross multiply. So that gives you -1 by itself. And then it gives you y times the quantity, -x² plus c. And when you're multiplied by a quantity, now you can actually get that y alone. And what do you do to get that y alone? It's division. So this would be -1 over the quantity -x² plus c, and that is where y is by itself. That algebraically is the correct way to solve that. Yeah.
If you do the reciprocal just correctly,
Okay, so yes, the reciprocal correctly would be to take the 1 and flip it over the whole thing. Yep. Yes. It's just when you take the reciprocal individually of the pieces that's illegal. You can't do that. Yeah, Ethan.
Can you take the negatives out since it doesn't apply, since c is a constant?
Yep. So in other words, can I multiply everything, the top and bottom, by -1? And the answer is yes. You can multiply the top by -1 and multiply by the bottom of -1. And then you'll multiply c by -1, which is still a constant. That's all legal. Okay. But that was really just so that the school would sign off on it. I don't think he'll really go to either of them. All right, here we go. Solve this differential equation and this time we've added a little twist with an initial condition. So we'll see what that has to do with anything once we get there. So first we want to separate. So anytime you see the words differential equation, that means that you've got to start with separating them. Sometimes it's really helpful. Some of the problems will say, the following is a separable differential equation. They put the word separable in there, and then that is really nice when they do that because that shit is like, oh, separate, separable, I can do that. So we cross multiply. So it's algebra first, a tiny, teeny bit of calculus, and then the rest is more algebra. So as we separate, it will become 2y times dy. This is the cross multiplying part, and then x dx. So that was a pretty easy separation. Then we go to the integration phase. So an integral on both sides. What do you think could be a mistake here? It could be, but that's usually not, sometimes, but there's actually a more basic mistake that people make at this point.
Take the integral on one side.
Take the integral on one side and forget to take the integral on the other. I see that a lot, okay? You've got to integrate both sides. Whatever you do in math to one side, you got to do to the other. All right, so our antiderivatives. The antiderivative of 2y is technically 2y to the second divided by 2. But if it's all the same to you, I'm just going to write y squared. And then I know that there's a plus c1, but I'm not going to be picky if you don't write c1 and c2, if you just go automatically to the plus c that you know is going to end up on the other side. So I'm going to save you a little time. This will become 1/2 x squared, or x squared over 2, and then plus the constant c. Because we have an initial condition, before you solve for y and get y alone, you want to actually solve for c before you solve for y. The initial condition is there so that you have a number to value to plug in for x, and you have a value to plug in for y, and that value will allow you to solve for what c actually is. Remember, what does c stand for, like graphically? Yeah, the thing that shifts the graph up and down. Okay, this is a graph. It's a sideways parabola. This sideways parabola is going this way. Okay, I know that because it has a y square. Oh, no, take it back. This is this is a hyperbola, okay, because both of them are squared. So this is a hyperbola that's going to be opening one side to the right and one side to the left. But the plus c is going to be shifting it up and down. And because I know exactly what point that it's supposed to go through, that'll help me figure out the value of my plus c. So I go ahead and I drop -3 as my y value, square it, and then I'm going to put 2 as my x value and square it, and that's going to help me figure out what c is. So that means that leads to 9 being equal to what plus c? 2 plus c. So therefore, c must be equal to 7. So then my last algebraic step is to solve. So y squared is equal to 1/2 x squared plus the constant, the specific constant of 7. And then I want to get y alone. And what's the last algebraic step? Square root, and what goes in front of every single square root has to be a plus or minus. And so y would be the positive and negative square root of the quantity 1/2 x squared plus 7. So algebraically, remember the plus minus, and then algebraically remember that the square root impacts the quantity 1/2 x squared plus 7. It's not going to be separate square root on the 7 and a separate square root on the 1/2 x squared. It is the square root applied to the quantity. Yeah.
How come this isn't a circle?
Because when you move x squared and y squared to the same, the only way for it to be a circle, it has to be ax squared plus by squared. It has to be a plus. And when we move this, if you have ax squared minus by squared equals c, that's going to make a hyperbola. And if you have the y is the first part, which is what this one is, that's going to make a hyperbola opening a different direction. So it's the subtraction that makes it hyperbola. Okay, great. All right, here's another one. Here's the same. We saw this differential equation earlier, and we practiced how to change that into a fraction, and then practiced how to cross multiply. And what we're going to be doing now is just how do we solve for the initial condition. So remember, the algebraic step first is always that separate. And our separation on this one turned into, we already did it, e to the negative 2y dy and e to the negative x dx. So that was the separation here. Then we have our integration. So drop an integral on both sides. Okay, Reagan, can you do the integral on the left side with the y terms?
E to the negative 2y over 2. Let's see.
Okay, e to the negative 2y divided by, and then I can read her mind. I know what she's doing already. There is a natural log e there, but she's already simplified it. And then you said the other thing that was there was, should be a negative 2. Don't forget the negative sign. And then she's right about there being a first c value. Okay, and then on the other side, we have a similar antiderivative, e to the negative x divided by the natural log of e, and then divided by negative 1, and that has a second c value. But we can consolidate all of that. Okay, the natural logs of e would all simplify to 1. Okay, so we can clean that up. And then, yeah, we can clean up a lot of this. So what I would say that we want to have this looking like is we want to have this be negative 1 over 2 in the denominator, and then put e to the 2y in our denominator. And then on the other side, we're going to have negative 1 in my numerator over e to the x, and then there's my plus c. Okay, here is where we pause in the algebra and we actually plug in the values of 0 and 0. If you proceed and go to getting y by itself first, it's not that it's mathematically wrong, it's just mathematically harder. Okay, so it's not wrong if you forget and you just go right ahead and I'm solving for c because you're in the groove, and then you realize, oh shoot, I need to solve for my plus c value. It's okay to do that, but the math, the arithmetic, I should say, turns out easier if you pause and do it here. So we're going to solve for c. And we're going to do that by changing x and y both to be 0. So when I do that, I'll have negative 1 over 2 e to the 0 and negative 1 over e to the 0 plus c. And that just is a lot easier in terms of arithmetic because e to the 0 is going to automatically be 1. So that's going to lead me to negative 1/2 and negative 1 plus c. And so if that's true, then what is my c value? Positive 1/2. Once I have that c value, then finish the problem and solve for y and getting y alone. So I'm going to slide mine over because I'm going to need a little bit more than you guys. So I've got negative 1 over 2 e to the 2y equals negative 1 over e to the x, and then plus 1/2. Now this has a little bit tricky algebra. I would love to apply a reciprocal to both sides, or I would love to cross multiply both sides. But I can't until what's true about the x side of the problem? Combined in what way though? I need a common denominator. Okay, I can't do cross multiplication. I can't do reciprocals unless I actually create a common denominator first. This is where your algebra is going to be harder than your calculus part. So the algebra means if I want a common denominator, I'm going to have to multiply this by 2 in the numerator and denominator, but I'm going to have to multiply that by e to the x. So I'm going to have negative 2 over 2e to the x, and then I'm going to have e to the x over 2e to the x. And getting that common denominator will allow me then to consolidate the two terms into one. So that's my next step, is I'm going to say, all right, plus, and then they share the denominator, 2e to the x. That will allow me then to either cross multiply or apply the rule of reciprocals. So the rule of reciprocals would say 2e to the 2y over negative 1, and then 2e to the x over negative 2 plus e to the x. The goal in doing that is so that I can get y by itself. It's this y that I want to get alone. So I'm going to, now that it's at least in the numerator, I'm going to want to get rid of this negative 1. I'm going to want to get rid of the 2. And I'm going to need to get rid of the e. I've got a lot of things to get rid of. Okay, cross multiplying also works fine. Okay, any suggestions now algebraically? You pick your favorite. What do you want to do next? You want to cross multiply? Do you want to do something else? Multiply both sides by negative 1/2. All right, so if I multiply this side by negative 1 over 2 and multiply this side by negative 1 over 2, that'll work, because what it'll do is it'll reduce the negative 1 and it will reduce the 2. On the other side, so I'll have e to the 2y will be all that's left. And then I'll have negative 2e to the x in the numerator. And my denominator, you could distribute it, or you can just leave it. It doesn't matter, really, if you distribute. I think I'm probably going to leave it out. If I leave that 2 out here, what do you notice else happens? It can reduce with that 2. Okay, so those would go away. So I think that would be what I would prefer to do instead of distributing. I would leave it out so that I could reduce those one to the other. Okay. All right, we're almost there. What's the next algebraic step if getting y is the goal? Getting y alone is the goal. Yeah, I got to apply a natural log, but make sure you do it to the whole quantity. So that would be a natural log applied to the quantity, and then on the other side around parentheses also you're going to be applying a natural log. So that's going to leave me with 2y is equal to the natural log of the whole quantity of negative e to the x over negative 2 plus e to the x. One reminder about the way algebra works is, although you have an e to the x in the numerator, and you also have an e to the x in the denominator, they are not reducible because one of them is part of an addition problem. And so you can't reduce when addition or subtraction is involved. So my last step would be, all right, well then the only thing I could do is put a 1/2 in front of this term. That would be simplified. That has y by itself. Keep in mind that, did you have an idea?
I was going to ask if we need to put this in absolute values.
No, it's not a result of a antiderivative, okay? But an equivalent thing you could do is something that would apply to the half. Do you remember what that half could do? What power it has? It could move back into the position of the power. So you could also write it as the natural log of negative e to the x and minus 2 plus e to the x to the power half. And even more than that, and if you didn't want to write it to the power half, another thing you could do is write it as a square root of the whole thing. That would also work. Those are all equivalent. Okay, none of those are going to count you as minus half a points or anything because those are all equivalent things. The only things you'll get docked on are the plus c's as well as like the natural log ones like we did on the homework, on the quiz, I mean. Yes. So like back here at the beginning, could you have done that? Yep. Okay. All right. Okay, this next one's an interesting one. We'll finish this up. We're getting close. You'll see this on your homework. This one we just need to tackle in terms of, all right, I'm going to separate and I'm going to integrate. All right, so the algebraic step of separating. All right, SK, why don't you take that one? Can you do the separation? Move things around and tell me what we end up with.
Move the x to the other side.
Okay. All right, so he wants to move the dx, you mean?
Yes.
Okay. All right, I'll move the dx to the other side.
And divide by y squared.
Okay, so then what's that going to look like? You want to read me the whole thing?
dy over y squared equals to x squared.
Okay. All right, and then I think you might want to make one more change so that you're dealing with all products and no quotients, no fractions. Think of that. I'll have Juliet try.
Why did the negative 1 I mean, why did the negative 0?
Yeah, I think that's going to be better for you in the long run, is to not use y in the squared in the denominator, but to have y to the negative 2. Right? The reason we do that is so that the next step, the only calculus step we have to do, so that it's easier. Okay? By making that change, that will allow us then to go to the integrate step. Okay? All right, so Evan, take the integration step. I'll put an integral on both sides. Okay?
Derivative, so it's y to the negative 1 over negative 1 plus c
Yep.
equals x cubed over 3. And then
Plus
plus
C. All right, so that's the only calculus step you need to do. And then I'm going to change his to negative 1 over y. Okay, this is the point where you want to substitute in the 3 and you want to substitute in the 0. You want to do that right now. So when we plug in 3 for y, we'll end up with negative 1 over the constant 3. And then when we plug in 0, we'll end up with 0 cubed over 3 plus c. So what does that tell you ultimately the value of c is? Negative 1/3. Okay, so c turns out to be negative 1/3. That's arithmetic. Okay, back to algebra. Negative 1 over y equals x cubed over 3, and then plus the constant negative 1/3. And thankfully, we have a common denominator now because the thirds are a common denominator on those two sides. So then we could consolidate this and write it as a common denominator. So I'd have x cubed minus 1 over the common denominator of 3. That just leads us to easier algebra when we're ready to solve. So we can apply the reciprocal rule. So that will be y over negative 1 being equal to 3 over x cubed minus 1, and then I just need to multiply both sides by the -1 to solve for the y. So that would lead me to y is -3 is the numerator, and then x cubed minus 1 is the denominator. Okay, any questions about that one? Okay. All right, last one. It's not as bad as you think. All right, so Kaylin, let's do the separate part.
So multiply right side by dx.
Okay?
And then divide the whole thing by the quantity 1 plus y squared.
All right, so I'm hearing you say dy divided by the quantity 1 plus y squared, and then what's left on the other side?
2x e to the x squared.
Yeah. 2x times e to the x squared and then the dx. Okay, good job on the separation. Okay, that looks great. All right. Okay, Julie, your one line of calculus. Pick one side. You don't have to do both. I'll just have you pick. Do you want to integrate the left side or the right side?
Left.
All right, she wants to do the left side. Okay, what is the antiderivative of dy over 1 plus y squared? It is something inverse. It's tangent. Yep. Okay. Tangent inverse of, good job. Great. Okay, that is tangent inverse. It's one of those special ones. Okay, doesn't have a square root in it, but like a square root would be the ones that would be either the secant or the inverse sine, inverse secant or inverse sine. Okay. All right, Stephen, how about the other side? Integrate. How are we going to do that?
Tabular integration.
Okay, tabular integration. Okay, that could be a possibility. You're thinking that because you see a p for a polynomial term and you see an e for an exponential term. So that could be a possibility. But I like his thinking, that he's thinking back, well, what have I learned before? Okay, because now it's like everything, oh, Julie had to remember the inverse of tangent. Okay, so that could be a strategy. I think you might run yourself into circles on that one a little bit. There might be one of the other strategies that's going to work a little bit better. A u-sub, Julie, where do you see a u-sub maybe working? Okay, the fact that x squared is here. And what's the derivative of x squared? 2x, which is here, and that's usually a good sign that a u-sub might work. Okay, so let's try that. Let's take the 2x squared, excuse me, just the x squared. There's not a 2. Take the x squared and claim that as our u. And if we claim that as our u, then 2x dx would be our du, which means 1 over 2x is the du. And I think that's going to really work out great for us because of the fact that we have the 2x in our value. So what we've got is 2x e to the u, and then substituting 1 over 2x du. So that's going to be a great way for us to eliminate the 2x from the problem altogether. So we just have e to the u, which needs an antiderivative. So we're looking at the antiderivative of e to the u is e to the u, and then a plus c. And then change that e to the u back. So the tangent inverse of y is equal to e to the x squared plus c. Now we don't have an initial condition. We don't have a value that'll help me with the c value. Yeah.
When you take the antiderivative of the left side, do you need a plus c over there too?
It would be like a c1,
Oh,
and then on the right side is a c2, and I just already combined them. Yep. So we don't have a plus c value to solve, so we can go right to the very last thing, which is the algebraic step of just solving for y. All right. What? Okay, how do we solve for y?
Tangent of both sides.
Okay, and not just the tangent of both sides, the tangent quantity of both sides. So then y by itself would be the tangent quantity of e to the x squared plus c, where c is part of the quantity that you took the tangent of. Okay, you better believe that if this is a multiple choice problem, then the option tangent e to the x squared with the plus c on the outside is also going to be one of the options. So that would have the person who had done everything right until the last step, and then an algebraic thing caught him at the end. So, yeah, okay, so it's not that. You're applying it to the quantity.